Dear students, we left our discussion at steady and unsteady hydrological models. So we'll try to understand what is the difference between steady and unsteady flows or parameters in the context of any hydrological process that we are trying to learn about. As you know, when we talk about steady processes for any variable x, that by definition means that rate of change of x with respect to time is equal to 0. Now, in case of hydrology, we would primarily deal with the inflows. And if we say that rate of change of inflow with respect to time is equal to 0, that means we are talking about the steady rate of inflow or steady rate of precipitation. And if we plot this, you would see that if we have time here and if we have I here, since this is not allowed to vary with respect to time, the variation would look like a straight line. Similarly, we can extrapolate this discussion to outflows and say that if del Q upon del T is also equal to 0, that means that outflow is also not changing, and hence we are going to get the straight lines here, that function is not changing with respect to time. Now, unfortunately, most of the hydrological processes that we deal in real life, they are not going to be steady. There would be some variation with respect to time. That would mean that when we are talking about precipitation will increase and then decrease. And as the precipitation is increasing, the runoff or the amount of stream flow that we will observe at certain place will also increase and then decrease. So if this is the variation of I, this is the variation of Q, both of them are going to be unsteady. And in hydrological models, we would like to capture at least some of this unsteadiness that exists in the inflow as well as outflow. And we will study these kind of variations using hytographs. That is how the precipitation is varying, hytographs and hydrographs. So hydrographs will tell us how the stream flow is varying, and we will talk about hytographs and hydrographs in much more detail when we go towards the subsequent chapters. Now, if we talk about increasing the complexity, we can always talk about the distributed non-steady models that will try to give us complete understanding of the characteristics of watershed in more comprehensive way. But you can clearly see that the number of equations, number of variables that we have to deal with, they are going to be large, and hence we have the models of all complexities. In this class, we will also talk about a real hydrological model, which would be a semi-distributed model, and we will try to simulate this non-steady flows both for precipitation as well as for outflows. Also, in addition to the time invariance or in addition to being lumped or distributed, there is another classification that exists in the hydrology that we should quickly talk about, is that whether our hydrological models are deterministic or they are stochastic. Now, when we talk about stochastic models, that means that our input is going to be some value, let us say IT, but the output in this case, it is going to be probabilistic. That means rather than having one finite value, it is going to follow certain distribution, which we typically characterize through the PDF. So if this is our probability of observing Q and this is the value corresponding to the Q, and we are always dealing with the probabilities, and instead of dealing with one specific value, we have to deal with mean, variance and other statistical attributes. On the other hand, in this particular class, since this is your first course on hydrology, most of our discussions would be restricted to the deterministic hydrological model. What that would mean, in case of deterministic models, if we know an IT, does not matter how many times you are going to run a model, your output is always going to be a point process. For example, if precipitation 20 mm happens on a given day, and you have set up your hydrological model that says that if 20 mm per day precipitation happens over IIT Gandhinagar, the runoff is going to be 12 mm per day. Now, in case of stochastic models, that 20 mm per day could result in the distribution, although this distribution is not going to change depending upon from what area you take a sample. That 12 mm sometimes could be 8 mm, that 12 mm sometimes could shift on the right side, which could be 14 mm, and the mean value may be centered around the 12 mm per day. However, in case of deterministic equations or deterministic models, we are going to always end up with one specific value, which is going to be 12 mm per day. Now, by default, whenever I will use the hydrological model in the context of present class, I would be talking about deterministic time invariant hydrological model.